So lightweight, compressible for good payload efficiency, inflatable to large scale, so that could be used to move sensors from place to place, and then the potential to degrade afterwards and not be noticed by the environment, I think are good reasons. That are some of that you could do with existing systems, but I think all of it together would be hard to replicate otherwise.
Hey everyone, welcome to It's a Material World. We're the show that uncovers why material science will change the world. Consider subscribing and hitting the like button down below. It would really help us out. And without further ado, let's get right into it.
Today's sponsor is Matmatch. With Matmatch, you can find materials for your projects in their free database of thousands of metals, polymers, composites, and ceramics. For example, you could search based on a given mechanical property, such as hardness or tensile strength, or simply search by name to find more information about a specific material. You could also find and contact suppliers if you have questions about a certain material, and join more than 2 million engineers and designers who use Matmatch every year. To join, just simply go to matmatch.com and start searching for free today. Hello everybody. Today our guest is Rob Shepard, a professor at Cornell University, where he leads the Organic Robotics Laboratory and has also co-founded the Organic Robotics Corporation. His work currently focuses on using soft material composites to redefine human-robot interactions in wearable robots and in patient care. Thank you so much for joining us, Rob. We're very excited to talk to you today.
Thanks, David, and thanks, Punith.
Yeah, of course. So first, could you give us a brief overview of what exactly soft robotics means and what this field encompasses?
Yeah, this is a field that has become very popular in the last 10 years, but has been around in the current state for about 30 years and has been under development for the last 150 years. And really what defines that development is our control, the synthesis of polymers. As a civilization, humanity's civilization, we've been using polymers for a long time, natural rubber to begin with, which is from a gutta percha tree. But we were very dependent on that alone. We couldn't modulate its properties. And also it would break apart into flakes very easily because it wasn't chemically cross-linked. And so,
real quick, can you define what cross-linked polymers are?
Yeah. So if you think of polymers as a bowl of spaghetti noodles, those are physically entangled. They're wrapped around each other. And if you pull on them, eventually they'll unravel and come apart.
Right.
But you can chemically cross-link polymers. And so these spaghetti noodles are then connected to each other with other much smaller spaghetti noodles. And so then you can pull on it and they'll stretch a little bit, but then they won't go past those chemical connections. The Dow Corning company chemically cross-linked silicone to create something they called silastic. And now we had very tough, very soft rubber that you could stretch a lot and it would come back and lose almost no energy in the process. So it stores a lot of energy, and when you let it go, it comes back. And most of that energy is given back to the environment without thermal losses to the rubber. And then after that, we start seeing silastic and other synthetic like polyurethanes being used in things like human interfaces with machines, like a prosthetic. It doesn't hurt as much anymore to wear a prosthesis when you have these very soft but tough mechanical insulators. And then later on, people like Koichi Suzumori started making machines out of these rubbers. Basically, and by the way, balloons have been around for a long time as well. And the first implementation of soft robots were balloons. There was McKibben actuators earlier in the 60s or 70s, I think, which were made out of not silicones, but might have been actually, I think it actually was natural rubber. And it was wrapped with these fibers that I think at around 30-degree angles, these fibers were. And when you pressurize this cylinder balloon, these fibers would reorient themselves and actually cause a contraction. Even though you're inflating the balloon, it causes a contraction. So you can pull on things very much like our own muscle works. And so these McKibben actuators were a very biomimetic, even have a similar force velocity curve as to natural muscle.
And real
And so,
quick, sorry to interrupt, but I have a feeling we'll talk about actuators a lot. So can you quickly define that as well?
yeah, actuators turn energy into motion.
Got it.
Mechanical actuators. You can also have other types of actuation, but the ones I'm talking about all the time is taking an energy input and turning it into a mechanical motion, then usually to apply a load to something and move it.
Got it.
So yeah, actuators are machines, and these machines that I'm talking about, balloons, they use change in pressure times change in volume as the energy input to cause a shape change, which then causes a load. And so in a McKibben actuator, you're applying like 30 psi, let's say, of pressure into this cylindrical cavity, which causes it to contract and expand laterally. And when it contracts, you can do like pull something like your muscle applies to your forearm to pull it in. So it's very biomimetic in how it worked. But then later on, Suzumori came around and started using silicones for smaller machines that didn't have these fiber encumberments. And these fibers make it so that it's less compliant we call it passive degrees of freedom. So an active degree of freedom is that for the McKibben is what you're pulling against. But a passive degree of freedom would be if you push it from the side, it can move as well. And it has an infinite number of passive degrees of freedom, can move around anywhere. But it's still, these fibers aren't that soft. They do have a high modulus of elasticity, which means that you stretch it a little bit, but it takes a lot of energy input to stretch it a little bit. And that's a high modulus. A low modulus means a little bit of energy of force input to get a large amount of stretch. And our skin is like this. It doesn't take much stress to pull our skin a lot. Mm-hmm. And so soft robotics for a lot of us is trying to create robots that interact with humans at the same level of stress and strain as our skin has. So these fabrics that McKibben actuators have are not that. They're very coarse. Suzumori about 30 years ago, 20 to 30 years ago, made these silicone tubes that he inflated and patterned so that they would move in a very biomimetic way. When you look at it, especially at the time when nobody had been doing this, it's like, wow, that's an animal, but it's not. It's just a balloon. And it's very soft. And if it wrapped around your hand, it would feel like an organism wrapping around your hand. So very, very interesting, but it didn't really catch on outside of Japan for a couple of decades. And I'd say that there's two reasons it started to explode in Europe. There was funding that the Italian Institute of Technology got, I think from the European Research Council, to explore biomimetic robots, and that resulted in something called the Poseidon, I believe is what it was called. And it was just a underwater robot, but it had very soft actuators. There's this person named Ian Walker who started working on tendons, like wires that you pull, and then they move around some compliant surfaces, like things that bend easily. Mm-hmm. And then and Ian was in the US, but he was doing this a little bit before the federal government in the US started funding through DARPA, this, which is a funding organization, Defense Advanced Research Project Agency, funding something called chembots, like chemical robots. And then this funded some work at MIT and Harvard that created these soft robots. And I was a postdoc there during an extension of that program, maximum mobility and manipulation, which turned these chembots into soft robots. And then, so now the US, the European Union, and Japan and many other countries started working on soft robotics. And now it's a worldwide phenomenon that is, trying to find its home. And, there's a lot of new concepts and sensors. So measuring the environment, much of the contributions in soft robotics is in tactile or touch measurements of the environment. And then compliant, infinite passive degree of freedom actuators for affecting the environment from that sensory input. And I measure success in a field by companies like has the, I mean, of course, there are many reasons to do research that isn't for commercialization, but when a field has become mature, it starts to produce technology that humanity can use to improve itself. And so then you start to see startup companies that are selling things using reliable manufacturing processes. And we're starting to see that in soft robotics. There's several companies that are coming up that are doing good work and, proving the utility.
That's a really, really detailed background. I didn't know it was so like intense and that it's been going on for hundreds of years.
A lot of
I
history.
get, yeah, I guess just to break it down a little bit, I know that you have a lot of experience working with the prosthetic arm. Could you tell us about your journey specifically about designing and implementing it, and kind of why soft robotics is such a big plus when you think about prosthetic arms?
Yeah. So the hit, like I was saying, the history of elastomers or rubbers in prosthetics is long. They're the first use one of the first use cases of silicones was in the interface of prosthetics with tissue to soften that impact. What has happened? We and others have been able to extend it from just being a passive structure to an active machine for interacting with the environment. And these passive degrees of freedom are increase the affordance or the ability to do the same task with less computation for manipulators. So now we can have a hand that's made of soft material, and we have ligaments and muscles, and the muscles, even when we tense our muscles, we can still pull on it a little bit. They're still compliant. Of course, it varies. Like the rock might be a different kind of thing, but most people, if you tense your muscle, you're still able to move them around a little bit. But I'd say that what soft robotics allows is a little bit of wiggle. So and feedback control that wiggle. So when you are plugging in something to a power outlet, you almost never get it in the first time. You get a little bit close, then you move it, and then you push it in. And so what we could do with this soft manipulator is grab on first. You can grab onto that power adapter without knowing exactly what shape it is and being able to over exert force on it, because your manipulator will fail before the object does. And so you want it to be able to grab and then wrap around it versus crush into it. And that's what the compliance allows. So first, you can pick up things, and that's how we work too. We over grasp. So you can do that now. And that's probably the major benefit. The next is that if you miss, there's a lot of degrees of freedom, active degrees of freedom, you can add to it to shift it into place. And the soft sensors that we've developed, the tactile sensation we've developed to complement vision, allows it, even with your eyes closed, you could feel that and then move it in. So I'd say it's the confluence of passive degrees of freedom for affordance, more easy integration of active degrees of freedom for wiggle, and then tactile feedback to complete the system. And you can do, because these materials are room temperature synthesized, mostly like rubbers, you can 3D print them. So you can create very complicated architectures for free. So complexity is for free, to quote Hot Lipson in 3D printing. So you can, whatever you want, you can just print, and it's the same as if you printed a brick, as if you printed La Sagrada Familia. So then you can get away with complex systems. So in what we call the adept prosthetic hand, we 3D printed most of it. And part of the 3D printed components was this rubber wheel. And we would take a tendon or this wire, and that wire was pulling at the end of the fingers. Much like our forearm, most of the muscles here are in actually pulling the tendons of our fingers here. Anyway, we use tendons to pull on the fingers of the hand, but these tendons are wrapped around these rubber wheels. And but the motors, instead of being in the forearm, we have the motors in the hand. So we have 6 motors in the hand. Each motor is spooling wire around a rubber disc. And that is our passive transmission system. And because we're using rubber as a machine in this way, it allows us to do something at a very small scale that normally a variable transmission system would be big. But here we wrap the wire, and that means because it's at a larger radius, it spools quickly, and then the hand can close quickly. But after it closes and starts pushing on something, it then pulls in on that rubber wheel, and then now it's at a lower radius and applies higher torque. So you can grasp quickly and then apply a lot of torque. And so it allows fast and powerful grasping. But the grasping is only as powerful as we tune it to be based on the compliance of the system. So we can pick up heavy wrenches. And I think that's about the limit of safety before we can start to actually damage tissue if we started to grab.
Gotcha.
But the whole thing, the whole hand, it has 6 active degrees of freedom, so 6 motors. The thumb can move in 2 directions, and the fingers just close. There's tactile sensing, so it can, and there's actually eyes, so the hand can see too. It can see when something's coming at it because it's got little fingers, and then it can start grasping on it, and then feel how much it's grasping on it for some feedback control there.
Wow.
Variable speeds, all because we can 3D print it, and we can reduce the complexity and size from using compliant mechanisms, which is from soft material like rubbers.
Wow. And when you define compliance, is that just the inverse of stiffness?
It is.
Okay, just making sure.
Yeah.
And so since these materials are so cool, can you tell us a little bit more about like what exactly are those elastomers that you're using in your lab?
Yeah, that's a really good question. I have talked about silicone before, and silicone is a rubber, and a rubber is an elastomer. In the particular case of this adept hand, we were actually using polyurethane. What is a polymer? A polymer is a macromolecule, or a large molecule of subunits called monomers. And but again, back to the spaghetti noodle analogy, they're just very, very thin, atomically thin spaghetti noodles, and they are above their glass transition temperature, so they can, meaning that they're mobile. They can move around. Heat or thermal energy is moving them around constantly, and because of that, and in many cases they're physically entangled, so they can't. It's hard for them to move, or they're chemically cross-linked, so they can't move beyond a certain extent. But they're always moving around thermally. And one of the really cool things about them is they are what we refer to as entropic springs. So these polymer networks are, as everything is, governed by enthalpy and entropy. But an entropy is how disordered a system is. But because there's so many, astronomical amounts of states that these noodles can be in, they're governed by entropy in most cases. And you can in many models, you can remove the chemical interaction potentials and just do the configurational space. And so when you stretch these rubbers, you're taking all these different arrangements they can be in and reducing them to few. The more stretched out they are, the less different states they can be in. And they don't like that. Things want to have the most amount of disorder, the most amount of states possible. So you're reducing that. And so you're storing energy in that. When you release this loading, now they can go back to their random, to their larger configurational number of configurational states. So you pull on it and then you let go, they return. That's using entropy as a spring. And so for whenever you mold these rubbers, you get a spring too. And so that's really useful. So when we pull on this hand, we only have to pull one way. And when we reduce the loading, the transmission system and the fingers, which are also rubber, want to return to their initial shape. So we get this extra degree of freedom, this from without the motor, due to the elastic restoring force. So anyway, rubbers are really cool. They absorb a lot of energy. You can stretch them over large distances, like you can stretch something like 1 centimeter to 7 centimeters and back again. That absorbs energy. And then on top of that, them being very tough, like we can take an impact, our skin can, they will restore that energy as well. Our ligaments, so a horse has this thing called a nuchal ligament, and when it leans over to drink water, it's got a big head. It stores most of the energy, most of the gravitational energy in that elastic energy of the nuchal ligament, and then it relaxes its muscle, and then its ligament allows it to come back up. And so most of that energy, and this happens all like in everything we do. Our body is just storing and releasing energy in very efficient ways. So we're not even close to the level of efficiency of using rubbers in our robots like nature is in organisms. So there's just even that, there's so much to do with in terms of improving the efficiency of our machines.
Wow, that's super cool. I didn't realize that, like, we can almost say that we're almost made out of rubber with the elastic restoring forces.
We absolutely are. And a new in the last 10 years, hydrogels have become not just for contact lenses, they become an engineering polymer. And hydrogels are exactly what our tissue is.
I guess you've talked a lot about all the benefits of rubbers and elastomers in the use of soft robotics. It kind of seems like these elastomers are kind of the only material for the job. So other than elastomers, have there ever been any other considerations, things such as shape memory alloys or other things that have similar properties, but now that I kind of hear about it more, it sounds like they would even fail to the task at hand?
Oh, not at all. No, I mean, thank you, David, for that question. So the good thing about rubbers is that they're intrinsically soft. So no matter what shape you make them, because the modulus is low, they're going to be soft. And they do have this entropic elasticity, which is a bonus, but you can architect softness too, which is an extrinsically soft system. So you can have you can take a sheet of metal or a rod of metal, which is not soft, and lathe it down to be, or process it another way to make it a very, very thin thing. And now all of a sudden it bends very easily. And so it's soft too. So even very high elastic modulus, and so meaning a lot of force to stretch it a tiny bit. Gigapascals would be a unit of very high elastic modulus. You can make those very soft just by making them very thin. And an advantage, you gave an example of shape memory alloys, is for a very low volume or low mass amount of material, you can get a high force. So you can pull, and they're used in aircraft. Sometimes you get a lot of load at the end of a shape memory alloy wire. And reversibly too. So if you apply heat, it'll contract, and let it cool down, it'll extend again. So you also get this resilience, but in a different way. So there's a lot of to me, it comes down to the processing. It's hard to, from the bottom up, manufacture systems using extrinsically soft things. But for elastomers, you can do anything you want from the bottom up, and it's still going to be soft. Now, is soft everything? No, in fact, soft is bad many times. Like we don't see any 10 meter, or we don't see any mammoth-sized worms. So
Yeah.
we have to have
Scary.
I would much rather see a mammoth-sized worm than a mammoth-sized mammoth in front of me.
Yes.
But there are huge worms underground. They're not that big. I mean, but you do get worms, something like this under the ground, because they're supported by the soil. But I mean, hard things are good. But I think we have too many. We solve too many of our problems with stiff systems because they're easier to model. While you were saying that I didn't realize we've had synthetic polymers around for this, long, the history of it. We've had metals for 10,000 years, 100,000 years. So we've been engineering with stones and metal for longer than we have with rubber. You could argue that we've been using wood for even longer, and wood is a composite of polymers. So, it kind of breaks down, but anyway, I think the main point is that rubber is easy to make things soft from the bottom up using 3D printing. And that's what we focus on. There's many other systems that are beneficial. They just don't work with the process we like.
So you're saying that there should be a better balance of, stiff systems versus like compliant systems or like softer materials, right?
Yeah, I think so. But then, somebody could push back and say, well, the market drives the need. And so what needs are there that require this rebalancing? And then on the other side of it, science and scientific efforts from research institutions are not beholden to the same thing. Like we don't necessarily have to um, solve an immediate problem. We're trying to discover new models and to be able to predict things and new knowledge that can be used for engineering purposes to create systems. But I'd say that we're at the point now where we have enough scientific understanding of these compliant mechanisms and sensors and the feedback control loops for them, that we can start to predict how they would be better than other existing systems. And for those cases, there are a few clear wins emerging. Some are in supply chain operations for pick and place of different objects. In fact, on factory floors, underwater robots where buoyant support means that you don't need skeletal systems and you can have very enduring large soft robots. In space is probably another one where mass and size constraints are severe in deploying things, and these inflatable structures can help.
Yeah.
And then haptics, so wearable systems, which are becoming more important for VR as VR and AR is coming out. Tactile stimulation and in prosthetics, which has been a problem for as long as humans have been around, and it's helping there too. So these are all use cases that soft robotics is being applied to very well and importantly, I think.
Cool.
Yeah, I just have a question. You just mentioned tactile stimulation again, and we were talking about it with the prosthetic. How exactly, if I wear a prosthetic, do I feel the touch of the hand if like the soft robotic is like most of my arm?
Yeah, this is an open area of research, and we haven't done it, but other people have. And so one way to do it, believe Dan Eagleman is the first name that's coming to mind, but in one system, you'll have like a patch that you will be in a different location from where your sensory input is coming. And that sensory input doesn't have to be where your prosthetic is. It could be vision, or it could be some extra sensory that you don't normally have, like infrared or seismic or whatever input, and then being output into a tactile stimulation. In the case of a prosthetic hand, you would want it to be the hand is touching and feeling something. And we have used stretchable fiber optic sensors for a hand that feels the environment. But the next step would be to incorporate that into some kind of tactile input to the human, which could be something that's vibrotactile, something that vibrates and that your phone uses. In the case of soft systems, there's a company called Haptics, HAPTX, that is using little fluidic cells or little tiny balloons that inflate to make it, feel like something's there. And the important difference there between vibrotactile and these fluidic systems is persistence of touch and large shape changes. So vibrotactile is just a vibration, and it can trick your brain into feeling like you've touched something like solid. It's pretty interesting, but persistently vibrating isn't a good. I think that representing things in VR with persistent vibration is probably not the right way to do it, but a balloon changing its shape to represent different things. And we did some work on this with NVIDIA research on a VR controller that changes its shape based on what you're seeing in VR. And it provided some pretty compelling data points. Haptics is a company that's doing this and selling it. And then like they have a demonstration. I haven't tried it, but one of my students has, where you can see a fox moving around in your hand, and it really feels like there's a fox moving around in your hand from the glove they have. So,
wow.
It's something simple, and, just using balloons to apply these pressure outputs. But that would be a very obvious way connect a prosthetic that can feel to remotely tactile input from, and the brain's plasticity is something that's being, researched, and it's, because we're so able to remodel our brain that it's perhaps you'd be able to immediately, eventually after learning for some time, immediately map a haptic response on like your back to your fingers touch somewhere else, but that hasn't been done enough to know for sure.
Wow. So are you saying that like potentially the future of VR could be being able to feel like familiar objects, just like, playing games or something like that using soft
Yeah,
robots?
I mean, I don't think that's my vision. There's I can't even remember the movie. An Enter Player One, I think, is a popular movie that like
Mhm.
shows the haptic suit. But that's just taking information. I love this interplay between science and art,
Right.
uh, and I think scientists have been working on haptics for a long time, but getting the artistic representation of the future is pretty motivational to communities. And but yeah, I think touch has to be a part of it. Our brain has large amounts of neural circuitry devoted to touch.
Mhm.
I've heard more from people who work in this space, as much or more than is devoted to vision, and I've heard from vision people that know it's blind. Anyway, this nobody knows for sure, I guess. But anyway, it's clear that if we as humans can't feel, that's a huge problem. I mean, I could argue maybe even a bigger problem than lack of
I
vision.
see.
So anyway, they both are very important sensory inputs. But in order to experience or immerse yourself in a virtual environment or even an augmented environment, I think touch has to be part of it. We don't think about it right now because it's hard to do. A lot of the vision problems are farther along than the touch ones. So we think VR is vision, but VR is touch. We just haven't gotten there yet.
Absolutely. Yeah.
Mm.
And so you briefly mentioned endurance as a characteristic of robots. And so you told us before that one of the main challenges your lab tries to solve is finding that optimal balance between a robot's endurance and agility. Can you give us an example of the trade-off that's made there in today's robotics and how soft robots could help with that?
Yeah, this is more about wheels versus legs. And are your well, if you know somebody who has a Tesla, that or anything actually, is autonomous vehicles aren't just electric, but it seems to be more prevalent in electric vehicles. But autonomy and wheels allows you to go 300 miles without touching your steering wheel. But you can only do that, as I like to say, because we spent like $1 trillion making roads, so things are flat, and we can use wheels on it. But if we didn't spend that $1 trillion, then we'd be using horses, and horses have legs, and that very adaptable to changing. You don't need to make a road for a horse to work, and that is what our postal service used for a long time before we had roads. But so they're very and we've seen legged robots. Like there's just an explosion of legged robots.
Mhm.
I think quadrupedal robots are going to be like quadcopters were 15 to 20 years ago. I'm just going to start seeing them everywhere, solving last mile delivery problems,
Mm.
especially pandemic related issues. So anyway, they're here, and they're going to be more and more. So, but right now they're limited to operating in a building for like 90 minutes in a pretty well-known environment. Um, what would be great is if we could fuse the two, like wheeled endurance with legged adaptivity, or agility. Uh, and the best examples of that are in our organisms. All of these systems, I think, could be made better with better perception of the environment, not just vision, but touch, and also more degrees of freedom instead of just a rubber foot, which they have now, little hands, arms. Anyway, just so we can improve these legged robots, as well as better energy storage. Um, right now, a lot of energy is donated for every footstep into the environment and not recovered. So, and there's just a lot of things we can do with hybrid compliant soft robotics with existing hard-legged robots and the control schemes that have been developed for them, and entirely new control schemes that will be enabled with new processing techniques like neuromorphic chip software and like brain-like computer processing. So yeah, the future of robotics is bright, and soft robotics will be a big part of it.
Wow. Well, if I'm sold on soft robotics, but I guess so far today we've really talked about a lot of advantages, and there really are a ton of advantages why you would want to use soft robotics. But can you kind of tell us about why soft robotics aren't prevalent? So, what are the disadvantages currently plaguing the area that you're trying to solve currently?
Well, I think that the mostly it's reliable manufacturing, and I think that's the most new things, new technologies. It's how reliably you can reproduce it. So even for our group, which is pretty good at making these things, if we hand them off a device off to another group that is like a traditional robotics group, and their experience is in DC motors. DC motors have been under development for 200 years. They'll blow them up. They'll break them. Even though they're very tough, they will find a way to break it. And it's just the reliably manufacturing so that every single one is exactly the same, and then the specifications for use, and then over engineering the system with safety factors so that they don't fail under misuse, I think is pretty much what's needed. And we have confidence here in that we make 1 trillion balloons a year. So we know, and they don't cost very little. So we know you can scalably and reliably produce soft systems. It was just that things are more complicated than a balloon. And then there's the integration and feedback control loops and integration of sensing. But injection molding, blow molding, most of the things we buy today are made. I mean, if you do in percentage, are made with injection molding, which is perfect for soft robotics. And so you see in leading order, Soft Robotics Incorporated is producing this pneumatically powered gripper that is working for adaptive grasping and supply chain management. It's not that complicated, from just looking at it, but reliably producing it in a way that adds value to the people who are buying it instead of a bunch of headaches does take significant engineering challenges. And so I think that's why there are certainly places you can't use it. I mean, a balloon's worst enemy is a needle. So, you have to think about all these things and define the niche for it. But there definitely is. And that's being proven commercially right now. And we'll see more and more examples soon.
Awesome. And one thing that was super exciting that you had mentioned before was like the space exploration and long distance underwater exploration. Can you walk us through the advantages that these soft robots would provide, like with a space rover that has to operate in this completely new environment?
Mm-hmm. Yeah, we were funded by NASA from their NIAC program a few years ago with Mason Peck, also at Cornell. And this was for making a underwater rover for Europa, which has an icy surface and a liquid ocean underneath. How you get through the ice to the ocean, not my problem.
Outside of the scope.
But because one of the likely first uses of soft robots will be in underwater vehicles, where they have the buoyant support. That means, the same thing is not just true for our planet, but other planets. A good thing about a soft robot is in some configurations, it can be almost a balloon, which is just a thin sheet of rubber. And and what you want is to be able to move it and then direct a sensor from place to place. That sensor doesn't have to weigh a lot. The propulsion, if you can use, I believe the term would be exogenous materials, or the materials around you when you are in the ocean of Europa, and you can deploy a minimum amount of mass and volume from Earth, then it's lower cost. Let's say you bring it, you somehow get it under the ice, and now you're in the ocean. You could inflate it with salt water. And then you could start pushing against the surrounding water to move to where you want to go to different locations. The amount of force it takes to move some of these soft actuators is very small compared to like a metal fulcrum type thing. So you could potentially generate the energy you need from electrolysis of water to create hydrogen and oxygen. There's however you get under the ocean, under the ice cap, you could probably also use that energy source to electrolyze water to create the hydrogen and oxygen. That would then be used to move the fish underwater, either through pneumatic pressure or fuel cells or combustion of the hydrogen and oxygen. We actually have an underwater combustion powered hydrojetting paper where we're doing explosions in a robot to push propel. It's
Wow.
pretty cool. But anyway, there's a variety, and by paying attention on how you engineer the motion of the rubber, you can turn a lot of these simple inputs into complex outputs that you could use for steering and getting sensing from place to place. Also, probably importantly, is we shouldn't try to destroy the environments we're going to, and NASA is very good about forward thinking of this, but the same robots we make could mostly be degradable in some way. So by having some understanding of what the material composition is, the environment, we could probably synthesize a elastomeric robot that could degrade into the compounds that are already there and not affect everything. So lightweight, compressible for good payload efficiency, inflatable to large scale, so that could be used to move sensors from place to place, and then the potential to degrade afterwards and not be noticed by the environment, I think are good reasons. That are some of that you could do with existing systems, but I think all of it together would be hard to replicate otherwise.
Yeah, that sounds amazing. I would love to see the robot that explodes some hydrogen to propel itself. I think one part of what you talked about was really interesting, that with organic robot or these smart robots, you could harvest materials on the plant surface. So I know we talked about maybe like wood, like collecting wood. Could you like walk us through like any other possible explanations and like go into that a little bit more?
Yeah, so I'd like to say that we do balance fun and science. So we like to speculate a lot, but at the end of the day, what we're trying to do is hypothesize, test, and build models for predictive purposes. But we also do this from first principles, and so instead of saying, well, this has worked, this has always worked, so let's keep doing it that way and improve it a little bit. We try to rethink the process and from the ground up and think of different ways to do it. So, and we use bio inspiration all the time. What we do, so this endurance versus agility front that we're trying to improve, organisms are great at it. We have very high efficiencies, system level efficiencies. Like a DC motor is actually like 90% efficient from turning electricity into motion. Our muscles are like 35% efficient. So a DC motor is more efficient than we are, but there's a systemic problems if you consider the whole thing, from how the energy is generated in the first place that it gets to the motor, and then how the motor is integrated into the system. So biology as a system is way more efficient than our human technology is. But we also have the ability to ingest energy dense chemistry. So a lithium polymer battery is 1 to 2 orders or 10 to 100 times less dense with energy than a steak is. So if we can eat a steak, which we, as hunter gatherers, we can get a lot of these chemical fuels wherever we are, then we can operate for longer. And so wood, we can't digest it, but if we apply a flame to it, the autocatalytic reaction produces a lot of energy. So if we could design robots to fuel themselves from different sources of energy that doesn't require plugging in, then we could get some of these endurance. We could get enduring robots that could operate for longer periods of time without having to to plug in. So, like climate change is a big problem, right? So I'm not promoting tons of robots burning wood, a few for persistent monitoring of the environment. Like another application for soft robots that we didn't talk about is in agriculture. Going right now, we have crop scientists that go out and do a few measurements every now and then because it's difficult and they have other things to do. They can't always be in the field doing things, or they can't always be in the forest. So, but if you could have robots that are patrolling areas, taking measurements continuously, we would have a much better idea and argue less about climate change, I think, than we do now. We would have continuous evidence over large areas. But then we'd have to, if we do it in the current way, our robots would probably fall over and not be able to do anything. But let's say we solve that problem, they still need to plug in every now and then, and we don't have power outlets in Siberia or wherever. So anyway, so this would be a way to the idea is not necessarily, I just use burning wood as an example, is just to design our robots to harvest chemical energy from the environment for longer periods of operation.
Wow. So you mentioned that, so this project is, funded by NASA. That's to go to, what is it? One of Jupiter's moons, Europa or something like that?
Yeah,
is that
Europa.
correct? Okay. Mm-hmm. So how do you approach the challenge of not knowing exactly what is in that atmosphere and what resources are there? Do you have a general idea, or how do you go about that?
I rely on space scientists to tell me what is there. I really don't know. I'm just going, and so they'll set just like any engineering challenge, you get a set of customer requirements, which would be defined by the space scientists we work with. And then we have within that our engineering characteristics that we map the customer requirements to, and then we can modulate those engineering characteristics to get something that is what neither side wants, but is the optimal between everything. And so usually how you deal with unknowns is by having redundant systems. And so in this case, we have been streamlining everything, and we haven't considered redundancy yet because we're just trying to get the minimal set of features to work. And after that, we'll add redundant systems to it. Yeah. So this is a question, not just about soft robotics. Everybody has to deal with this. And usually it's redundant systems. In nature, multifunctionality is part of it. And the more, I don't know if this is a rule, but it seems to me that the more complex the organism, the less redundancy and the more multifunctionality there is, which so a worm you can cut in half and then I guess there'll be two worms. But yeah, you can't cut us in half.
Not easily, at least.
Not easily, yeah. Right. So anyway, we have and lizards, anyway, things can regrow limbs. We can't regrow limbs. I guess there's some trade-offs in terms of the complexity and the benefits of the complexity versus the simplicity and the redundancy. And that is in design, that would be integral versus modular design, coarsely. And one of the premises we have as a research group is that in order to get this endurance, this better combination of endurance and agility, we have to have an integral system with very complex multifunctional use of features, which is why we do 3D printing, because these complexities are easier to deal with when you 3D print everything.
But yeah, there's fantastic cutting edge research that you and other people in the soft robotics field are doing. If I was a material science engineering student now entering college, what advice would you have for me if I wanted to get into your industry?
One is the field of robotics is largely undefined, but it has been around for decades, and there are many roboticists in that field that will has a feeling that all the problems have been solved, that actuation and sensing and stuff isn't a problem, and they're wrong. It is a big problem, and so instead of taking the challenge of embodiment to heart, they put all of the effort in the brain, and say AI, or machine learning, or maybe not even machine learning, but anyway, the algorithms in the central processor are the that is what has to be solved. But soft robotics says no, you can offload a lot of these computational challenges to the body and the interaction of the body with the environment. um, so I'd say if you end up meeting some of the entrenched people that might be negative about it, you should kind of ignore them. There's somewhat pessimistic and there's optimistic. Um, but the pessimistic people add a lot of value in forcing you to think about what you're actually doing. But if it's all pessimism, then you just have very slow and iterative improvements on what already exists. Optimism says, I'm going to create something new. And but if you do that blindly without understanding the thing why you're doing it, then it takes a while for what you do to matter, if it ends up mattering at all. And so there's a blend that matters. So
Mhm.
I'd say that whatever uh, new materials are very important for robots, and you should work with people that have a good blend of optimism and pessimism, whether that be a group that has a distribution of optimistic people or people themselves that are self-critical, but don't let that get in the way of trying out new ideas.
Cool. Well, thank you so much, Rob, for joining us today. We really learned a lot about soft robots and their several applications. It was super intriguing. So I really appreciate you coming onto the show.
Thank you. Thanks. I enjoyed being here.
Thank you for tuning in to this episode of the It's a Material World podcast. If you enjoyed the show, consider subscribing and hitting the like button down below. If you want to meet other passionate material scientists and engineers, join our Discord community using the link in the description. If you have any feedback for us, we would love to hear it. We want to grow this show with our community's input, so comment below with your thoughts on this episode and what topics you want to see us cover next. We'll see you very soon, and in the meantime, go change the world.